So during this course, we're going to be looking at 3 different types of wastes. We're going to have solid, liquid, and gaseous. So we've already looked at water, so that was the liquid waste. Now we're going to look at solid in this lecture. And I'm sorry, I'm just trying to get onto, okay, it doesn't want to let me make a red marker today. Okay, so, oh, there we go, it's just being slow, sorry. Okay, so in terms of waste, so waste is going to solid waste. We're going to define solid waste in terms of obviously anything that's solid, but more specifically, we can break it down into these types of things. So each municipal waste, any waste has a code. So it's GW, any general waste, and it has various different codes. So 01 being municipal waste, all the way through 10, 20, 30 for commercial, organic, and construction and demolition waste. And then the 50, 51, 2, 3, 4, you'll see are more common things like paper, plastic, glass, metals, and tires. And then GW99 is a total. In South Africa, so this is the South African data, which I got from the website at the bottom there. I recommend you go and look at that website or that PDF document that you can download. This table is from there and other information. According to that, and I think this data was 2017, which was the latest version that I could find when I was looking through it, there's 54 million tons of waste that is produced. Some important things to just quickly note on this table, which I'll leave you to read through or pause the video and have a look at again. Construction and demolition waste, there is no creation of it because obviously it's something that happens after a building has been demolished. We're not producing it, so these are the production values that we've got here. How much do you produce? How much do you export? In some of these numbers, it's very small because there's no need to import waste or export it. And then more importantly, how much do we recycle versus how much do we landfill? So recycling, how much are we able to reuse? So you'll look down all at the bottom. We are very good at recycling tires or recovering rather, maybe not necessarily recycling, as well as the glass metals. They're quite high in the 70s, construction waste is 90s, whereas some of the other things we are not very good at. So it's only 10% of commercial or industrial waste, no municipal waste, according to these data, because this is the number that we are landfilling. Okay, so this municipal waste is everything other than what's down at the bottom here. So 100% of that is on landfill. The balance of these numbers here on the last column is obviously 100 minus this value to the left. So in terms of in South Africa, what is our municipal solid waste like? What do we generate in South Africa? So we are down here in a light green, so not the best in the dark green. So we're roughly 0.5 to 0.99 kilograms of waste per capita, so that's per person per day. So we are almost 1 kilogram of waste per person per day. So it's still, if you try and think about a kilogram over a year, that number gets very big very quickly, as we had in lecture 1, where we were showing how much you could get, waste was filling up football stadiums and how deep it would go to that effect. On a global scale, though, because we are a fairly poor country, we don't have as much construction, various things like that. We are still, as you see, developing nations. There is the green of Africa, the green of Asia. Compare that to places like America, Canada, some of Europe, as well as Australia. They produce a lot more waste than we do. So what we want to look at today is just to simply introduce you to what solid waste management is. What should we be doing with our garbage? What is the garbage? And we've already been through some of that stuff, those things rather. I'm going to introduce you to the 3 R's, and later on I actually think it's called the 4 R's, not the 3 R's, so just double check that when we get to that slide later. What are landfills and composting as 2 of the options for solid waste in terms of getting rid of it, and then also to introduce you to RDFs and the environmental impacts. So we'll get through later what exactly is an RDF. So I showed you on a previous slide that America is very keen to, so not very keen, they are a big polluter, a solid waste polluter. So they are very keen to show that they are doing something about it. So 1990, this is the USA, they have the Pollution Prevention Act. So I'm taking this wording because it's some nice wording out of the act, and we'll get to a local scenario on the next slide. So in terms of what the Americans, the USA, this act says, it says that pollution should be prevented or reduced at the source. So if we don't have the pollution at the source, we don't have to worry about what do we do with it at the end. So things like this where you should be preventing it at the source. So let's not be polluting at the factory gate itself, or if we can reduce packaging and waste like that, that would also be a way to reduce it at the source itself. We know that pollution is very difficult to get rid of completely, but the pollution that cannot be prevented should be recycled. And all of these things should happen in an environmentally safe manner. So I have deleted some of the words environmentally safe manner, but these apply to everything that we talk about today, not just on this slide. Okay, so pollution that cannot be prevented or recycled should be treated, again, in an environmentally safe manner. Disposal or other releases into the environment should be employed only as a last resort. So we don't actually want to be landfilling. We don't want to be putting things back into the rivers, the oceans, or onto a landfill site. It's only as a very last measure. So try and reduce things before we get to that point. In South Africa, we are going to again come back to Nema. So Nema, as a reminder, was the National Environmental Management Act. And in this instance, we have a specific Waste Management Act of 2008. So this act is here, what we've said, and you can read this properly, was to reform the law regulating waste management and to protect the health and the environment from these solid waste measures that we are looking at today. A further important part of Nema, the part of Nema which is not specific to Nema, but it's a concept that comes across in many other countries and in many other discussions, is the polluter pays principle. So the polluter pays principle is saying, in Nema it states that a person who causes or has caused or may cause significant pollution is responsible for that pollution. They must take responsible measures to prevent it, and if it comes to it, they are the one that needs to pay for any remediation or anything like that. So if you as a producer, if you're in a factory or an industrial facility, are able to reduce your pollution, you need to reduce it at the source, which is exactly what we said in the previous slides, but it gets down to that it actually comes down to money as well. There we have the saying there, the polluter will pay. In terms of solid waste, we can divide it into various different types. So it's typically subdivided into residential wastes or non-residential wastes, depending on its source. So is it coming from residential or non-residential? In a previous slide, you already seen, I think it was, that we also sometimes we call it industrial wastes. So you'll also see other subdivisions. These are the two main ones, residential and non-residential. You may also hear of even further subdivisions of industrial or forestry waste or very specific types of different wastes. We'll only refer to two of them in this lecture. In South Africa, mine waste, so that's from all the mines around the countries, account for most of our waste. We also have quite a bit of waste from the oil and gas industry, as well as waste from the wastewater treatment plants. So we said last week, or was it the week before, that wastewater treatment plants have a lot of sludge that can come off it. We can use anaerobic digestion to get those solids into a more usable form, but just by a sheer volume, there is a lot of solid waste from wastewater treatment plants as well. So I've already said that we are going to have residential or non-residential wastes, but we can also categorize waste in terms of what exactly it is. So we'll start on the right-hand side here, and we have a municipal solid waste, so it's often abbreviated to MSW. So if you see MSW, municipal solid waste, so that's the stuff that we have. So this is typically residential waste, which can either be garbage or food waste, the things that you are throwing in the bin every day, or we can have water treatment plants and non-combustible trash. So these are typically separated onto a second type of municipal solid waste. We also have hazardous waste. So there's various different types of hazardous waste, which I'm not going to get into today. And then there are also other waste. So the construction industry, we've already said has a lot of waste. We have auto bodies, so sorry, that's cars and things, or industrial waste. So here you see there's a different type of, we've already mentioned industrial waste as one of the subcategories as well. In terms of what are we going to do with this waste? So the vast quantities of waste, we can't just put it in a hole forever and ever. It's going to take up too much space. So what exactly are our options for disposal? The first one obviously is that put it in a hole option. So landfilling, we simply dig a hole or put it in a pile somewhere that is safe, away from anything that can cause harm. So preferably not too close to sensitive environments or people, and put it in a hole, and we'll get to that later. Or the second one is we can incinerate it. So incinerate it, and we'll get to this one later as well. We are simply going to burn it. If we burn it, we no longer have that solid mass. We may have issues with gaseous emissions, but this incineration option will take up less land space. Okay. Many landfills have approached full capacity, so it's always a problem of where do you take the waste, what do you do with it. So finding new spaces for landfills. I'm not going to offer my land for a landfill anytime soon, not that I have any land to offer, but that's the approach that many people would take. We're not going to, why would we want to have these dirty, smelly things near us? So the capacity and where do we put the stuff is often a problem. I've already said incineration can pose a risk of air pollution, so we're converting our solid waste pollution into an air pollution. Ideally, though, we don't want either of those, so we would like a zero waste approach. So zero waste approach, either we reduce it at the source or we look into recycling. So recycling of all materials back into nature to recycle it back to nature or back into a marketplace. So we either can reuse or we find some use for this old material so that we can aim for a zero waste economy. In order to do this, we want to have an integrated waste management strategy. So the industry should use these processes that make the least possible waste. So if there is an option of A or B, we should look at the one that uses, and this is probably not just for solid waste, but any waste. If there are two options, we should look at which one is the cleaner technology of that. So this is termed cleaner technology, to reduce toxicity, less packaging, product reused, and the like. Anything that can be used again should be taken out of the waste. So this comes down to, it's termed the resource recovery in bullet point 2, or just waste minimization or recycling. So this is going to require some form of removal of the useful waste from the general waste. So there's some sort of selection, or how do we take out the useful plastics that could be recycled, paper that could be recycled for resource recovery. Okay. If we have landfill as a problem, one of the solutions to reduce the land volume space issue is to compact. So some waste can be compacted, and I'm sure you've already seen this. Milk cartons, for example, seem to be the very good one in my dustbin at home. That takes up a lot of volume, yet all it is air inside it. So if you can somehow squash it, take the lid off, squash that milk carton, put the lid back on again so it's no longer taking as big a volume. We do this on a big scale. We can be compacting it for less space for the same amount of rubbish. That's a very bad example of the milk one, because we can recycle some of those cartons these days. Okay. In terms of what we're looking at in terms of this integrated solid waste management, there is a form of a hierarchy. So the most favorable one here is going to be reduction. So if we can reduce at source, as we already said, the amount of waste we've got here, that is the most favorable option. If we can reuse it, so simply not having to make a new thing of whatever we have, or we can recycle, the third most favorable option, recovery, and then disposal. So we are going to get back to this later, but maybe I'll just mention it now while it's here and start just explaining the difference between these four things. So here we can see our R's: reduce, reuse, recycle, recover. So there are the 4 R's that are going to come up later on. So that's why I said there were 4. They're not necessarily 5. So, sorry, 4, not 3. So I can't remember which one is the one that is often left off. I think it's recovery. Reduce, reuse, recycle are the 3 R's. Recovery is the 4th one. Reduce is fairly obvious. We're going to have less of the product. Reuse is often repurpose as well. So if you have a something and you have used it in its original case, how can we reuse that? So the example is something like a yogurt tub. You've used a yogurt tub to have yogurt in it. We've eaten the yogurt. We can now reuse that yogurt tub for something else, wash it out and put it back in our cupboards, and we can now use that as some form of container for food at a later stage or something like that. So that is reusing. Recycling would be taking that yogurt tub, sending it back to the factory for them to then melt down and make a new plastic tub. So it's not throwing it away onto landfill, it's actually sending it back to have it remade or reused into I shouldn't use the word reuse, that's the one above. Remade into something that it was before. Okay, so that would be going back to a factory to get remade. Recovery is something a little bit more complex, where if, let's just say, for example, a very simple example, we keep on the yogurt tub, and let's just say, for example, that the lid, we can't use the lid, but we can use the tub. So we can recover one part of the product, and then the rest is disposed of. So this would be more applicable to things that are much more complex than a yogurt tub, things like cars or TVs where we can start breaking things apart and we can recover certain aspects of a single material or a single product, and then we can either reuse, recycle, or do something else with a part of a product. So I've already mentioned source reduction is a very key one, so that was the first one, so I'm not going to spend too much time on this. Please pause and you can read through strategies that we've got here. There are, however, some green production strategies that are going to be important. So when we talk about green strategies, we often speak about environmental strategies in general. So if I say that it's green engineering, it's green anything, it's typically an environmentally more sustainable way of doing this. So some of these strategies could simply be material selection. So which feed material is going to be more environmentally friendly or environmentally safe for the environment. Which, if I've got a choice of starting materials, so it could be simply plastic or some form of bioplastic that's degradable or more environmentally friendly, I can have select the material that's most suitable for the job. Another strategy for this is to have the product system life extended. So instead of using something once, I use it more often. So instead of buying a cell phone every 2 years, I can buy a cell phone every 4 years. As the example, that just doubles up the length. So that means that the world would only need half the amount of cell phones if everyone bought a cell phone every 4 years instead of 2 years. And that would be applicable to everything. So do you really need something as soon as you think you do, or can you stretch out the life of everything? And this would apply to clothes, to things in your kitchen, to everyday items. Can we extend their life so as to reduce the source? Okay. A third way for product strategy, for green production strategies, is to look at the process management. So the effective management of raw materials, energy input and output, or use of more efficient motors to control processes. This step down at the bottom here is process engineering. So process management, how can we get something to be more efficient? So we put a raw material into our chemical process, or not a chemical, any sort of process. It could be metallurgical or chemical or manufacturing, industrial. If we can put a material in to make cars, to make something else, and we only have 10% waste coming out instead of 50% waste, that is all an engineering efficiency and process management to reduce the source right at the beginning and reduce the solid waste. So here, as I said, we now have our 4 R's. So the 4 R's, as we had put that diagram: reduce to save money, waste minimization; recover at the point of generation; and reuse, we can reuse it again. The last one is recycling. So recycling is a little bit more complicated because it can involve people now needing to take things back. So recycling would be the collection and subsequent processing of any used product into a new product. So I already said plastic food containers like the yogurt tub. You can either go back into another yogurt tub, or we could be looking at it into a park bench. So the problem with recycling is that sometimes we can't just simply take a product and then recycle it back into the same thing. If I have white printer paper in front of me that I want to recycle and I've scribbled on it, it's very difficult for the paper manufacturers to then make white paper out of my old white paper again. It might be possible to make cardboard or newspaper, but often there is a loss in quality of things. This also applies to glass. So white glass is very difficult to recycle back into white glass, but it's easy to get white glass back into green or brown glass. I just want to, I'm having a look at these points before I flick over to the next slide. One of the issues here is that you need a dependable market. So often voluntary public, this grammar doesn't look that great. There's often nothing in it for the public to help recycle, so it's just in the best interests of the environment that you recycle. So sometimes if there is no dependable market and people aren't willing to recycle on their own, there are some payback schemes involved. So examples of this are when you take your glass bottles back to the shop, they give you a deposit back. So that deposit scheme is a way to get the public, not voluntarily, but sort of encouraging the public to help with recycling. And important, this should always meet legislative requirements. As a further note on recycling, and this is not always true, but it is possible that recycling may not be the best way to go. In some recycling options, it might mean that there are more processing steps needed to recycle a product than there would be to make the product from a fresh raw material. So if the product is a renewable source, so such as trees, and we're making paper, I'm not sure if this is true, so don't quote me on this, but let's just use that as the example. Trees being a renewable resource, it might actually be that paper is easier to make as fresh paper than recycling. So I have been to, actually it was last week that I went to a paper manufacturing mill, and recycling of paper actually is quite easy. So I'm not actually sure that this statement here that paper recycling is not effective, because I think it's very effective. It does not it does not always take more steps, but it may take more steps. So the key take home from this slide is that you need to look at both recycling processes rather, as well as normal processes, and compare the two. One of the ways to compare the two is going to be through things like carbon footprinting or water footprinting or life cycle assessment, which we will get to in one of the later lectures in, I think it's 2-3 weeks time. In South Africa, recycling is going to become a more common occurrence because we're about to get legislation that's coming in that requires manufacturers to trace and track all their products and ensure that they are returned back to them so that they can be recycled in an efficient manner. So this is called the extended producer responsibility, which means that if you're making paper, glass, plastics, anything like that, you will be reporting as to how much you make and then how much are you going to recycle as an industry and how much is being recycled. So there are targets. So these values I couldn't confirm before I updated these slides from a few years ago. So I don't know if these numbers are actually true or not, but the idea is that there is a lot of potential still in South Africa as well to start composting. In particular, we have home composting. So any of your organic matter, you could actually compost at home. So make a useful product without worrying about landfill space. Paper, glass, plastics, we can also separate those at source or separate those before landfill, and we can still recycle all of those types of things. In terms of recycling, why should we recycle? So we all know that it is potentially going to save things. How much does it save though? So there are some examples here. Just randomly, one recycled tin could save enough energy to power television for 3 hours. Again, I don't know how true these numbers are, but it's always, if we start adding these up, it's always interesting to see how much you could save. So one recycled plastic bottle could have enough energy to power a 60-watt bulb for 3 hours. So one recycled plastic bottle, there's some people that are going to drink 2, 3, 4 of these a day. If they're not filling them up just with tap water, there's nothing wrong with tap water if you're wanting to drink some water. 5, 6 of these a day, that's the electricity that person would use for lighting in that day if they just had to recycle those types of bottles. Further on plastics, 1 ton of plastics can be equal to 20,000 2-liter bottles. So 20,000, one plastic bottle is fairly light, but when you add 20,000 to them, that's how much, if you're wanting to get up to 1 ton of plastic, that takes the equivalent of 20,000 2-liter bottles or 120,000 carrier bags. So in terms of how much plastic South Africa produces or how much waste there is, if you can now flick back, I can't flick back, go back to the original slide. So how many tons of plastic did we say there was in South Africa that's being produced or landfilled? So if we now go back and calculate how many 2-liter water bottles is that, sorry, not 2-liter water, 2-liter any bottle, or how many carrier bags, plastic shopping bags are those? Okay. The problem with plastics is that some of that ends up in the ocean. Most of it is all of it is recyclable, but there are very different types of plastics. So when you hold your water bottle up, you'll see a recycling logo. It's the 3 arrows in a triangle. And inside that, there's 1, 2, 3, 4, 5, 6, 7, the different numbers for the different types of plastics. So you can't put the different types of plastics through the same process. You have to separate all of these different types of plastics before you can recycle them. Some of the more common types of plastics are PET. So just note that's a typo in these notes. It should not have a second E. It's just polyethylene terephthalate, which I can never pronounce properly. High density polyethylene, polyvinyl chloride, low density polyethylene, polypropylene, and polystyrene. So you can see there some of the uses for this and how you can recycle it. So looking at this one, the PET has a high recycling potential, whereas you go down to the polystyrene. So polystyrene is often the foam trays or hamburger boxes. These are rarely recycled to these plastics. So because it's rarely recycled, this is where we're saying that we can change the solid waste at the source. You'll notice that hamburger boxes now are almost never in polystyrene anymore. They are now more often in cardboard boxes, as well as the egg cartons. Egg cartons are often also in paper or some sort of paper mulch sort of things. Mainly because polystyrene is rarely recycled. It's probably one of the more difficult ones to recycle as well. So one of the techniques, so this is now a new thought now, a new line of thinking, new topic. One of the ideas with solid waste management is to try and manage the amount or the processing of solid waste is to have something called a solid waste transfer station. This is a facility where the municipal solid waste is unloaded from smaller vehicles or collection vehicles. It's often held there for a short while of time. It can have separation at these sort of areas. It can have not necessarily recycling, I don't think, but it has various sort of intermediate roles before it gets put onto larger long-distance vehicles to take to landfill or other treatment disposal facilities that are further away. So every Thursday, every Wednesday, whatever day the municipal collection comes around from Pick It Up in Joburg, they take it in those smaller trucks, they take it to a solid waste transfer station where they can do sorting and selecting. So I'm not saying they do it in Joburg or they should do it in Joburg, but this is just the general idea across the country. At these sites, they can then have a separation, but then also more importantly, instead of having all of these small trucks going very far distances, they can have a big truck. I'm not actually 100% sure what happens in Joburg these days, but I know in Cape Town from that solid waste transfer station, it actually gets put onto a train and then it gets railed up to one of the landfill sites. So it's a bit more efficient to have it on a train. You can have as many coaches in the back as you want, instead of having these smaller vehicles that have to go backwards and forwards. The pros of this is that you can combine loads of several individual waste collection trucks and you can save money, so you don't have to have these guys going long distances. You can have one truck driver collecting in the streets of the residential areas, going a short distance to drop off, turning around and coming straight back again to collect the refuse from the next set of houses. It can also reduce the total number of trips traveling to the disposal site. So now we're only going halfway, a quarter of the way to the site, and we're leaving it up to the larger trucks to go all the way out to the further sites. So we're again saving the environment by not having all the air pollution of it. The theory of this, though, is that it can cause increased traffic in local areas. So you're going to have, wherever this transfer station is, you're going to have all of your rubbish trucks coming through and clogging up and congesting the traffic in some centralized area. It is also a problem, a potential problem, that depending on where the solid waste transfer station is, because it has to be somewhere central, it's not far away, again, it's an issue of those that live nearby are going to have the smell or other problematic issues, or problems rather, I see the word is that's used there, living near them. Is there going to be a smell? Is there the wind comes up and blows small bits of the solid waste into your garden, or what's that going to be? So there are also cons to this idea. So if we could find a way to sort out instead of having the problem of solid waste in the first place, are there ways that we can get around the solid waste, not just from a volume point of view, but just also from a general environmental point of view? The first option is to compost. So compost, we've already been through anaerobic digestion. The composting process is the anaerobic degradation of organic materials under those controlled conditions that do have air. So if you have an end product that's rich in organic matter, so this is often food waste. So food waste is actually quite a large contributor to solid municipal waste issues. If you have things from vegetable shops or other high organic rich material, you can add that as a soil conditioner. So that organic matter has nutrients such as nitrogen, phosphate, and potassium, which is advantageous for soils, but as I say here, as the note here, just as a way, let me just find it quickly. The levels of key nutrients are too low to compete with commercial fertilizers, so we would never use this on farms where we are trying to make crops for the country, but it is still enough nutrients for us to throw in our gardens or to have our own little vegetable garden in our backyard. The problem with composting is that with anything that's organic or natural, it can be affected by temperature, moisture, pH, often the availability of oxygen, or whatever our natural surroundings can give us. So the speed or the usefulness of this can often depend on what bacteria and fungi can grow in those environments. There are ways to get optimal temperatures, moistures, and pH, but then we are starting to add on our own level of human interaction, if I could call it that maybe, or engineered solutions. And as soon as we add engineered solutions onto this, we're probably going to be needing infrastructure, electricity, water, and various other things which need to get piped to wherever we are going. And depending on the scale of the system, this is just going to add, or could add, more environmental problems than it could solve. Okay, so we already mentioned some of the factors that affect composting, so please pause here and read through the temperature, pH, oxygen, and nutrients, and how these would be affected, and what is good and what is bad. We've already mentioned landfills. So landfills are probably the most common common way of getting rid of solid waste. So all of us know that we put our rubbish in a dustbin, somebody comes to collect it, and most of that ends up somewhere in a big hole, or we hope it ends up in some big hole that is then carefully managed and we don't damage the environment further. The problem is that landfills can be expensive because it's not simply a hole in the ground. It is a hole in the ground that is going to be maintained, and we'll get to that in a slide a little bit further on. But there's also the whole infrastructure of getting the things to the landfill, maintaining it, and various other things. So it's not always a cheap solution. It's possibly one of the cheaper solutions, but not the cheapest way of dealing with this. The cheapest way would not be having any solid waste management in the first place. It also has some short-term effects, so it can be a nuisance with odors, pests, litter, and smoke. So landfills often have birds that fly over, that are trying to pick at the little bits that are in there. The odors that come from it, when the wind starts blowing, you get all sorts of things flying all over the place. So there's also the issue of, so to reduce that, a lot of these landfills then cover certain parts of the landfill with sand to avoid the trash being blown around. But then instead of the trash being blown around, you get dust that could be a nuisance as well. A landfill is also a potential loss of recycling. So anything that just gets dumped in a landfill, once it's in that landfill, it's very difficult to get it back out of that landfill. So you're not going to, it's uncontrolled recycling. Depending on what you've thrown in there, it could also catch fire. So there's often papers and things like that in there that could burn and catch fire. And these landfills are big. So if that had to catch fire, it would be quite a nasty thing. Leachate, that's the water. So let me just highlight that one there. Leachate, any rainwater that falls onto a landfill or any liquid material that is in the landfill itself will seep through the landfill down to the bottom into the soil, or could get into the soil, which that liquid then gets into the rivers or various other systems. So it's a bit of a complex issue that you need to take care of. So this leachate, I had a friend when I was at Varsity used to call this the dustbin juice. So depending on what you've thrown in your dustbin, when you try and empty it out afterwards, all that juice that's left at the bottom from who knows where it comes from, organic matter that's left there, that all gets into the groundwater. So there are also long-term effects. So obviously that leachate, the dustbin juice, you're going to end up with groundwater pollution, so that's seeping down into the groundwater. You could also have surface water pollution, and there's just general degradation of the environmental area. Okay, this is often used as a last resort, particularly for hazardous materials. So there's certain hazardous materials that you can't do anything with, and you have to landfill them. So if we don't want those hazardous materials to get into the groundwater or into the leachate, these then need to be put into sealed containers. Depending how dangerous or hazardous they are sometimes even put into concrete slabs. So you not only have a hole in the ground, but you have to take your hazardous material into a container, in a concrete container. So it's taking up quite a bit of space to get rid of whatever your hazardous material might be. So this all comes down to now, how do we actually construct this landfill? So we've already mentioned this leachate, the water that's coming through here, or the liquids that come here, are going to be critical in managing the environmental situation of this. So that moisture content that we talk about is very important for the proper decomposition, but also we don't want too much of it to leak into the ground. So let me just take a step back and say that and just go over this again. Moisture is important for the proper decomposition. So water is a lifeblood for microorganisms. Microorganisms are often in liquid systems. They need water to grow and breathe. And if we are going to have micro decomposition or biological breakdown of certain materials, these microorganisms need water. So we need that water in there. However, that water that percolates through the surface and that is aiding the decomposition is going to end up in the local groundwater if we don't collect and treat it somehow to avoid that contamination. So to do that, we are often going to use a flexible membrane liner that collects the percolated water. And I'll get to that in another slide in a bit. Okay. The second thing is that when we have these microorganisms doing their thing to decompose everything, one of the byproducts is often going to be methane. So that decomposition, either biological or chemical, and is with the methane formation, we are going to have some form or some way of collecting this methane so that we don't have either a toxic environment or we don't have this igniting and causing any sort of fire or explosion. How big do you need your landfill when we are constructing this? This is all a matter of estimating the rate at which the waste is discarded. So I don't know how much pollution, we know how much waste Johannesburg has. The problem is what is that going to look like in 5 years' time, in 10 years' time? So we need to estimate the rate at which it's discarded now, how much we think is going to be discarded in 5 years' time, 10 years' time, work out the volume that we need for this landfill, how long will it last, can we get people to rather reduce their waste so that we can extend the life of this landfill for a little bit longer. There's also a factor of waste density. This density depends on how much you compact it. So we talked about compacting earlier on. So typically the waste would be thrown onto the landfill and we'll get heavy machinery rolling over it just to compact it a little bit. But how much do we spread it? How much do we compact it? Do we have a soil layer over it to avoid things blowing away? So that's all factors that need to be taken into account with landfill construction. In terms of how we now set this up, we're going to build this. So typically the landfill is actually dug down, so it's not level with the ground. So this red line that we follow here is digging the landfill down to a certain level. Once we get to that level, we now can't just start piling things on top, but we need to start preparing the lower levels to receive the solid waste. So the first one is typically I'm just trying to look here, it's the red line here. So it typically starts with a compacted clay and synthetic liner. So if we can get clay so that we don't get anything seeping through the clay, we can use that as our first insulation layer. Secondly, there's typically a synthetic liner, I don't want to call it a plastic, but it pretty much is a plastic liner that then goes at the bottom of that so that any waters don't permeate through into the groundwater, but instead we can direct the waters. So as the engineer, you can decide which way do you want the waters to flow. So let's just say in this example, it's flowing down towards here, and we can have or engineer a way to collect the water or any of the leachate that comes through. So that's going to be how you start this off. Typically, let's just look at these poles on the right here, these pipes, these tubes. Typically, because we often have groundwater in the area, so this isn't to scale, this could be a lot deeper than this. We want to make sure that nothing is leaking, so there'll be typically a groundwater monitoring well, so you drop a well so you can pull water samples out to check every now and again. What that would do is there's no way of knowing if there's a leak or a break in this lining here, this red layer that we've got. If there's a leak, we'll never know unless we're monitoring the water. So if we can monitor the water at the top, at the bottom, several other points, we can see which way this pollutant or the leachate is going through if it is coming through. At the same time, there would typically be a gas monitoring probe, so you can see if there's anything else happening in terms of gas. So both on the left, on the right here. Okay, so that's just not in the landfill, but somewhere outside. Once you've got that in place, we can start putting the refuse in. So it would typically start on the one side, and you'd fill it up. You'd probably fill it from the bottom first and build up and build up. When it gets to its maximum height, it's not uncommon to see that there is some form of covering that is put onto this so that it sort of starts to rehabilitate and everything inside is kept in place. So in this example, they're saying there's a granular drainage material, so I suppose that's some sort of gravel or stony particles type that. Often there's some soil, sorry, underneath that, the first one, the black one, is a low permeability cap. So something that can be, in this instance, we do want the waters to go through. Okay, so we said that we want some moisture in here for the bacteria to do their job. So this might be more like a felt type substance, a cloth type thing. Very durable though. And then on top of that, and this looks very thin here, it's often a final clay cap with vegetation. So at this stage, it's possible to start putting plants on it so that the vegetation on top of this green layer here looks the same as everyone else. Depending on how this is done, typically this isn't going to be mounded up into a big fat mountain. That's why you dig it out to start with, so that then this level doesn't come up to a huge Table Mountain sized hill, but it's something a little bit smaller and a little bit more manageable. While this is going, there also might be a stormwater control berm. So this is simply I'm trying to think how to explain this now, a sort of a wall, I suppose. So a wall along here, so any rain that you might get in here would gather along, and this engineered berm, you can then direct the rainwater to whichever way you want to go. So if your leachate collection sump in this bottom thing here is also working properly, everything will fall down through there. But just by mass balance and flow, water is going to flow on here. It's going to seep out the side here, so you're going to get some water collection on the side here, which you want to then get rid of as well. As a note on these systems, so when these systems are put into the ground or they are developed, the local weatherman will be contacted to determine whether this is a net rainfall area, a positive rainfall area, or positive evaporation. So if we have a higher evaporation rate than a rainfall rate in the area, it's typical to see that you're losing water to the atmosphere. If that is the case, you would not expect anything to actually collect in this leachate rises, so you would not need as big a collection point here. If you're in an area where there's a lot more rainfall than there is evaporation, so the net water onto this is greater than leaving, then this leachate will definitely collect water, and you would need to design it such that it is bigger than your zero rainfall or net zero rainfall areas. Okay, so this is something similar. So you can see this is now done again. We've got our lined system. I'll let you look through here. The gray is the garbage or the trash that we've got in here. If we are going to be taking gas off, so I skipped that one on the last slide, I think. So when we take the gas off, if you're going to have methane, depending on how much methane you actually get off, if this is something fairly big, you can actually generate electricity from it. Okay, so so what is the scale of these things? It can vary. I've been to one where this was 300 meters wide, and they hadn't decided how long it was yet, because luckily for them, this was in Cape Town, they had a piece of land that could just go on and on and on, depending on when somebody bought the land at the end, and then the municipality told them to stop. So 300 meters wide by a lot more long, you probably can get enough electricity off here, maybe not to plug into the electricity, into the Eskom system, but at least run your own little buildings, because you often have a building here with somebody managing the site, making sure everything is still working properly. Okay, so this is again, just you can pause here again, just see what the different layers are that might be in a constructed landfill site. The different levels of that, yeah. I'll let you pause there. Okay, so if we're having a landfill, once it's done, we are ideally wanting to have decomposition in the landfill. This is going to come about in 4 phases. There's the anaerobic phase, the acid phase, there's unsteady state methanogenesis. So I've been talking a little bit too long at one go, I'm losing my words. And then the last one is the steady state methanogenesis. Okay, so each one of those is going to have different set of conditions when the bacteria are doing different things. Aerobic is obviously when you have oxygen and you're going to have breakdown. Unfortunately, depending on what level you are in the landfill, so sorry, I can't go back, as I said, if we're at the bottom of the landfill and we've been piling things on top, there's no more oxygen for these microorganisms to actually do their job. So once that happens, we then have an anaerobic phase, because now we've got no oxygen, because what was on the top of the landfill is now at the middle of the landfill or slightly lower down. So we then have a second set of conditions for fermentation into simple organic acids. After that has happened, we're going to get an unsteady state system where the methanogens convert any organic acids from the previous stage. They're going to produce organic acids. Those organic acids are going to convert into methane and CO2. Okay. As a note here, this phase can last for months. This version is unsteady because it's the startup of the system. Once you get going, and it's been going for a few months and things hit steady state, then we hit the next phase. This all depends on the availability of moisture and the nutrients. It can go on for years, and it could be decades before the process is complete. So you might know of some areas that have landfills that have been closed. So once a landfill is closed, it's been covered up, and there's grass on top of it and various other things. Nothing happens on top of that landfill for many, many years to come. That's because of these 4 phases, particularly the last 2. So you don't want to start having a landfill. And often these landfills are out in the middle of nowhere. Johannesburg grows. Suddenly that middle of nowhere was something in the middle of something, and it suddenly becomes valuable land for somebody to build on. We don't want to build on that because of these 2 phases. And while anything is happening with decomposition and any changes to the landfill, the land, I suppose, can shift and move. So if we had to go and build something on the landfill, it could sink or move around, so it's not a good idea. I do know of some landfills. I know there's one near where I used to live that was closed down, and then about 5-10 years later, they put a golf driving range on it. So it's still a valuable piece of land, so people can, and it wasn't really on it. Where you hit the wall from was on the side, and you hit onto the landfill, because this is now a nicely manicured piece of lawn. You wouldn't even know that there was a landfill under it at one point. Another option besides landfilling is to convert some of this waste to energy combustion. So this was the last point on our outcomes list from earlier on. It's the refuse derived fuel, so it's RDF. So I'm coming back to somebody who was asking me about plastics, and can you burn plastics because then we don't have, or we can get energy from it. This was an alternative energy solution. So yes, the answer again is you can burn plastics. You can burn various other things. In this instance, though, we're not looking to burn plastics as a way of making our primary energy source, but this is a way of reducing our solid waste. So instead of having a large landfill area, we can now have a smaller landfill area. But as a bonus byproduct, we also get this fuel. So we can recover energy from combustion. Okay. So electricity generated from a typical, so it's a 100,000 ton per annum facility, could be enough for the electricity for 10,000 houses. So go back again to the first slide. There's a 100,000 tons per annum. I can't remember the numbers on this. So how much did we have in South Africa for the municipal waste? If we had to convert that on the ratio of 100,000 tons per annum to 10,000 houses, how much energy would we be able to get from that landfilled material? When you do that maths, it's not going to be nearly enough for everyone, but at least it's a start in terms of energy, but more importantly, it's a reduction in the solid waste. So basically, what we would do is we would burn some of these things, and there are various different ways that we can burn the solid waste. There's gasification, pyrolysis, so it's with oxygen, without oxygen. We could just burn it through straight combustion. And from that, we can produce a low-pressure steam, which we can then use for heating. And I don't think in South Africa we really worry about the low-pressure steam for heating. But more importantly, we can drive turbines. So anytime that you have steam, you have a high-pressure gas, put it through a turbine, we can then power a generator. Okay. One of the issues with this is that you can't just throw anything into these combustors. So you need to know what exactly it is that you're putting in there. So certain plastics you might not want to put through there. Or if you've got metals that are going through there, metals are not going to burn. So there is some sort of classification that's needed. So the classification, as we point out here, is required to determine the feasibility for combustion, but more importantly as well is that to separate the things that can burn versus the things that won't burn. If we do that, there are, however, concerns about air pollution, burning of plastics and things that are going to cause toxics in the environment or in the air. Which we get to in the next slide as well, I think. Okay, not yet. Okay, so strengths and weaknesses of RDFs, and I've already forgotten what RDF stands for, so this is why, again, we have that list of acronyms that's on that online page, so we should actually all go and update that again so that we can all remember what it is when we go and look to it. So some of the strengths, just to highlight some of them here, please read through all of them. It can be integrated, so we have front-end recycling activity with energy recovery of the balance. So these collection stations that we were talking about earlier, if we can have a station there, we can have a separation station where we have a combustion site, so we can combust things at that site or recycle at that site. Then whatever we need to send to landfill is hopefully reduced. Okay. The organic fraction of combustion is very good. It can be recycled anaerobically through composting or, through anaerobic. So this is a good thing to have in here. However, okay, so there are some other positives. Just trying to see which one to highlight here. It often means, so one of the downsides is it requires a market for the fuel. So if you're going to be, or for the energy rather, so if you have electricity that's being generated, can you just plug it back into the Eskom grid? Or are you going to be powering a specific industrial site or a few houses? How do you get the energy back into a system? Okay. It also has, and just coming down to the bottom one here, it can also cause more damage to the boilers, mainly because of we don't know what is in certain of this wastes. So depending how well you separate it or you classify your waste beforehand, if you're just throwing any old rubbish, literally and metaphorically, into this system, it will damage your pipework faster than other fuels when you know exactly what's in it. Okay, so here's the slide I was thinking about earlier. So there are, however, environmental impacts of this waste to energy process. And one of them is, I'm going to jump down to here, is the dioxins and furans, so the waste byproducts that come about through the incineration or the burning of through combustions. So solids and gases are produced from combustion, so you're not going to get rid of everything when you combust, so there is going to be some ash left over that does need to be landfilled, which is a little bit lower. Those solids are more manageable than the large volumes before you burnt. The gases, however, can be a problem. So there may be highly toxic compounds from this incineration. I'm just trying to see, particularly in this one, there are dioxins and furans. So dioxins, they have been observed to cause cancer. So that was a study in 2003. They've also been shown to cause immune system problems in fish, birds, and mammals. They can affect cell growth. Oh, excuse me. Okay, so there are some issues with burning. There are also other impacts, or other problems rather. The first one being that it can concentrate the heavy metals. So when you had a large portion of solid waste before burning, after you've burnt, all of the heavy metals are now in one single source. So this could be a good thing because now you can control it, but now you have a concentrated heavy metal stream which you need to do something with. So they're lead, zinc, and cadmium. It can, though, however, it may not be concentrated because it could form part of the gases. So there are reports of things like mercury. I know that sort of being ending up being airborne. So if you have an incineration facility or a combustion for energy recovery, the mercury then ends up in the gases. It then goes to the nearby neighbors and drops down and sits on surfaces in the nearby areas. Okay, the additional reason there is that high temperatures, most metals will vaporize. Okay, I think some of this is repetition now, or it's kind of obvious from what we've been saying, that when we burn this solid waste, it's going to form ash. That ash we can collect it as fly ash as well as bottom ash. Both can be contaminated with those heavy metals or with the dioxins and furan. This ash, because it's such a fine particle, it can easily become airborne, so that's going to lead to respiratory problems. If it has toxic compounds, it needs to be treated as a hazardous waste. And if it's a hazardous waste, as I said earlier, you can't just take it straight to a landfill and dump it. You're going to have to put it in some sort of container so that it doesn't separate out from the other products, and that any water that runs through is not going to leach it out into the environment. There are some additional solid waste management techniques that we could also look at. The first one is immobilization. So that is where waste is converted to a more stable or insoluble form. So depending on what you have, for example, here you could add lime to a sludge to decrease the ability for it to flow or leach through the system. There's also encapsulation, so you can literally coat the waste with coat it with an inert or durable material, so that's putting something around it so that it can't move in some form of a capsule, and that could be a large or a fairly large or a smaller system. So macro encapsulation, this is what I was meaning there. So this is used in South Africa. We actually put a drum. So this is also I was talking about earlier. We put things in a drum surrounded by concrete in a reinforced concrete block. So this is typical for hazardous waste, particularly nuclear type waste. You want to put it in a drum surrounded by concrete so that we can't leach that out or nobody can get to it accidentally many years down the line. Okay. And then solidification, waste can be converted into an insoluble rock-like material. So we can mix it with cement. So you put it into cement so then it doesn't, so it's now a solid, it's not little bits of solids, and there's no way for things to get through it or to mix with it or for it to blow away. So now what can you do? So I think some of these things are fairly obvious. So obviously buy durable items, do recycle. So if we can, don't buy water bottles new water bottles every time you have water, rather buy one container that you can refill, rechargeable batteries, reduce junk mail. I think this should probably come out now because this was back in the day when everything got sent to you through a post box. Lobbying for trash separation and recycling, choose items with minimal things. You can also compost your yard or food waste. And I'm sure there are other things on this list that you can think of that you're probably already doing or that could be quite suitable for your neighborhood. There are also several untapped opportunities. So some of these things are being done to different sort of levels. So these are things that you could be looking at not as you as a student when you go home this evening, but these are things that you could possibly do when you are an engineer one day in a few years' time. So there are certain items that are more easily recyclable than others. So I don't want to go into the pros and cons of these because a lot of these items or these technologies are proprietary to the companies and they are progressing fairly rapidly. So I don't want to tell you that something is wrong when the current technology is actually a lot better than when the slide was put together. So for this week's material, I don't know what to say about this. So let me start again. The material for this week is covered in the textbook. It's covered in page 601 to 676. But please, can you tell me if your textbook actually has pages 601 to 676? I have a copy from the bookshop in the Matrix, the one downstairs. I forget its name now. I bought a copy of this textbook at the beginning of the year, and I opened this textbook up on last week sometime, and my textbook stops at page 600. So please, can you tell me if your textbook that you have in front of you actually has pages 601 to 676? I don't know if we need all of those pages, but those are the pages that the table of contents at the front of the book says are useful. If we can find those pages somehow, or if somebody has those pages, I will make a plan to let you know which pages are useful and which ones aren't, or I'll make another plan on somehow getting something to you in terms of a textbook. But like I say, please let me know if you can actually access those pages in your version of the textbook. The one that I've got is the one with this cover. So if you've got this one, New International Edition, you probably also don't have those pages. Let's hope somebody has those pages so we can actually read what the textbook has. Thanks.